Hey everyone, and welcome back to another episode of the QRL Show, the place where you come for the crypto and stay for the quantum. On today's episode, myself and Michael Strike from the QRL team, I are joined by several guests for what is the first ever QRL Post-Quantum Panel. In a moment, I'll touch on what the panel discussion is going to entail. But before this, I'll quickly introduce our two guests, and then I'll let them elaborate on their backgrounds each. But the first is Anastasia Marchenkova, quantum physicist, engineer, been involved in building quantum computers at Bleximo. She also has a really cool and creative in-depth YouTube content that covers all of this type of material. What am I missing here? Quantum researcher, alum of Georgia Tech, University of Maryland. Anastasia, I'll let you fill in some holes in a minute. But also joining us is Konstantinos Karagiannis. He is the director of quantum computing services at Protivity, spoken at tons of conferences around the globe. He is, everything from ISF World, Security Conference or Congress to hosting his own podcast, which is the Post-Quantum World. Konstantinos, I will let you fill in much more than that as well. But first off, Anastasia, Konstantinos, really good to have you with Michael and I to have a fun post-quantum discussion.
Welcome.
Happy to be back.
Good to be here. It's nice to know everyone involved.
Yeah. Well, it's been it's a busy year as every year is in the space that we're at both the intersection of, you have obviously quantum computing, progress on our side where the blockchain where that intersects with, and just a lot of excitement, a lot happening, but there's also a lot of noise. So part of what we'll be talking about today is trying to make some of these things a little bit more digestible for everyone. But before we jump into any questions, Anastasia and then Konstantinos, can you fill us in? I know I gave the high-level spark notes of your backgrounds, but could you maybe for a minute or two give us a little bit of context for the viewer? I know some people in our audience are going to be familiar with you based on your past episode with us. But yeah, fill in any holes and we'll take it from there.
Sure. So I've been in quantum almost 15 years now. So I started in quantum telecommunications and doing neutral atom quantum memories, so very hardware based. So going back to the crypto side is kind of a natural loop back. I was very involved in the startup world, still am very involved in the startup world, obviously being based in the Bay Area. For my PhD, I really wanted to move over to trapped ions. So I worked on that for a little bit, then moved into superconducting qubits, then moved into algorithms work, both quantum and classical computing algorithms as well. I worked with HPC and graph theory work. And yeah, kind of been around all up and down the quantum stack. Obviously, then got into the communication aspect. I've had a blog on quantum since 2015 because I realized that people weren't really communicating quantum for the engineer that maybe doesn't have a physics background. And I truly believe that once we have quantum computers in the world, we're just not going to have enough physicists to be able to run all of them. So we need to really empower the people to actually be able to use it. Just like these days, you don't have to know how to build a computer chip to be able to program something, right? The same thing needs to happen to quantum. So that's my journey. Startups, education, quantum, all over the map.
It's a solid diagram and a cool one how it intertwines. Konstantinos, let's port it over to you, and then
sure.
That will lead a nice context-wise into the conversation.
Yeah, I started in quantum back at Brooklyn Polytech eons ago, and I then shifted over for a while. I was interested in both quantum and I was interested in hacking. Those are just two passions I always had, kind of always have been there and are still there. And then there really was no quantum computer that you can do anything usably with at the time. So I ended up spending a lot more time in the InfoSec world. Spent many years doing that. And then as it started to look like these machines were coming on the horizon, I kind of shifted back to warning folks around 2012 or so, started really warning folks that this was going to become a reality and encryption would be threatened one day. And then all of a sudden, we were starting to see use cases that weren't related to cryptography. So that was a pretty exciting time to kind of be involved as all that kind of rose. So now in my role, I still do both. still helping companies with a threat to cryptography, and also building use cases to do things with these machines.
Yeah, no, thank you. Appreciate giving us some added context. Michael, I think we have quite a number of questions and directions we could take this conversation, but really to lay out for those viewing, kind of our intention is throughout each of these questions, we really just want to not only cover some of the advancements, implications of post-quantum technologies and what is to come, what's here present day, but making it kind of approachable, but still touching on the technical aspects. Michael, do you want to kick us off with a first question or two? I know we kind of already touched on what kind of inspired both of our guests to get into this role where they are and their expertise. But Michael, if you want to start out with a question, and we'll just lead from there.
Sure. Why don't we just do a quick explainer of how we first got involved in quantum tech. And I'll go first. I'll be pretty quick. I had actually first heard of quantum computers in 1997. I remember the conversation because I was arguing with another tech about special relativity, and I knew very, very, very little at that point. I was just I was building PCs. I think I was maybe 19 or 20 years old, and I remember bringing up quantum computer, and he also brought up 3D cubes. We're supposed to be able to have this was 97. We're supposed to have 3D cubes now where we're using a laser, and the angle of incident, angle of reflection are such that we should have been able to store great amounts of information. Well, that one didn't quite happen, and haven't really heard about it since then. But quantum computers are getting a lot of buzz. And I work obviously at the intersection of blockchain and quantum, and I love relativity. I love physics, and I love talking to people about physics. I'm passionate about it, and to me, this is really just about understanding our place in the universe. Ultimately, trying to break things down into things that we can understand. Yeah, so that basically became my interest in it. So, Anastasia, how did you first get into this? What brought you here, either from like a philosophical or even theological or whatever perspective?
Yeah, my story is always very disappointing to people, right? They're like, how did you know quantum was going to become a thing, that it was going to kick off? I didn't. My dad was a physicist. He was the coolest person ever, right? So I was a kid, everyone for show and tell brought in their dogs. I brought in my dad to do physics experiments and show. I was like always climbing. There's a photo of me when I'm like 4 years old climbing on the cryostats in the lab. So I spent all my time around scientists, engineers growing up. So I was very lucky in that aspect to just know that path even existed. And really that's the way we got to the US, right? Like based on education and having those opportunities and being able to bring that to the US. And then, I did declare as a computer science major in school. I did robotics when I was in high school. So I definitely wanted to do that first of all. But then I think I got like 110% in my first computer science class, and I was like, maybe this is a little too easy. Like, I feel like I'm not being challenged as much, and I really want to use computer science as a tool. Instead, I actually then switched to bio, was really interested in genetics, bioinformatics work at the time, and then still was like, wait, biology is all about memorizing 1,000-page textbooks. I don't want to do that either. And then, made my way over to physics after that. I think I just took physics 1 because we were required to take it at Georgia Tech, and I was like, oh, well, I'm good at this, but it's actually hard and I have to work at it. So I did that for the first kind of year in school. Then I was hopping around different research labs. I did a little work in chemical engineering as well in transdermal microneedle research, which again was a great experience, but was a little bit more mechanical in that way, right? A lot of data, which nothing wrong with that. But I really enjoyed building with my hands with my robotics background. Started reaching out to people in the physics department. The first person I emailed said, no, you need to have taken optics before you join the lab or some other class. So it was really like, you can't work in this lab until you're a 4th year. The second person I emailed was a quantum telecom lab, and they said, you can solder. Great. Okay, come in tomorrow. You have a role. And that was pretty much it. And very lucky for my advisor at that point. He was very involved with making sure that we were I mean, we were treated like full members of the lab, even as undergrads. We were in there all the time, had our own keys, in and out, and just spent a lot of time there. And yeah, very, very lucky to be in that space. And I just very much was like, this is cool, this is interesting, this is hard, let's dive deep into it.
That was not boring whatsoever. That was pretty amazing, actually. You had it sounds like you had not just the genetics, but also the environment, from your dad being a physicist, but also the right environment to cultivate. That's rare. So I think that's awesome. Konstantinos, please. Yeah, I know you have lots of interesting things to say.
Yeah, with physics, if you think about these computational paradigms of the stack and everything, everything I was ever interested in, it would always be about what's the lowest level of abstraction. How low down can you go? And somehow all paths always pointed back to the same thing. If you're interested in something like hacking, you go down the levels to machine language, eventually you get down to the transistor, eventually you start to get the quantum effects. You're interested in how the universe works, eventually you get down to that smallest level of abstraction. So it kind of all pointed to the same place. And that it was just super intriguing. And then I was lucky enough at a pretty young age to come across quantum and its real weirdness. I feel like physics students in general should be taught quantum, at least some element of it first, just because it's so intriguing and interesting. Like I think it might suck in folks that didn't even know it existed, So I was lucky enough to come across the weirdness of like the double slit experiment and all that good stuff at a pretty young age. So it kind of hooked me that there were other things going on there. I found David Deutsch at a young age, which is kind of difficult to process, right? You come across him and he'll say 100 words, and trapped in there is the wisdom of 4 million words somehow, and like just densely packed. So his interest in making these machines that might potentially prove the existence of the multiverse, I don't know, it was way too intriguing to pass up. So that's kind of like the earliest thing that like hooked me there.
I love what you said about peeling back, trying to get to the root of reality. I was a couple of years ago. I remember this. I was called a reductionist versus a holist. A holist is comfortable looking at a system as a whole, and then just knowing that it works and feeling comfortable with an abstract, contentment. Whereas the former is more of trying to break things down to their basic constituent components until you can start to finally build your knowledge back up. And as an engineer, as a problem solver, I always found myself much more of a reductionist. So I took it as a compliment. I'm not sure it was intended to be that way. But that means Ryan, if it's okay with you, I'll start off with our real first question here.
Yeah, no, that's fine with me. And then I think we just do a little bit of back and forth.
Yeah, let's do that. Yeah. Absolutely. So for people that are new to quantum computers, how do you explain what they are? And I'll give the best description that I've come up with so far, and you guys probably even have better descriptions. If someone's asking me for the first time, I'll explain that transistors and vacuum tubes, the integrated circuitry that we have today is very deterministic. Input in, program, same output. Input in, program, same output. Whereas quantum computers tend to be more probabilistic and less deterministic, that they're based on the analog wave functions inherent in quantum mechanics. In other words, just really strange, weird quantum stuff. And you might not always get the same answer, but that's my very condensed explanation. You guys probably have some insight to help me do my job even better on explaining how quantum computers work, and I would love to hear it. Anastasia, why don't we start with you?
Yeah, definitely. I mean, we've gone through, we've said this 100 times, like the way they explain the ones and zeros, but I recently in April was at RPI for a talk, and we really talked about CS education, what computer science students should know about quantum as they start getting into the field. And one of the things I really thought about there was, I don't really care that they know all the math behind it yet. What I really want them to know is what problems that quantum can solve. And this generally goes back to my philosophy. I've been working a little bit recently in things like thermodynamic computing. So I've been kind of diving into the next gen computing paradigm. And I really think we're going back to kind of the ASICs era, right? So I kind of say at the beginning, like, quantum computers are going to solve different problems. than classical computers can, right? And I really want to make that clear at the very beginning, where I say quantum computers are like more similar to GPUs, that GPUs accelerate graphics and are working for certain problems, but they work in conjunction with CPUs. Quantum computers will do the same thing for a subset of problems. And the reason they can do this is because of these quantum principles of superposition and entanglement, which I'm sure we're going to get into and explain a little more there. But the idea is, and then go into the ones and zeros, right? So the digital, the binary 0 and 1 is really a voltage, right? And so with quantum, we can do superposition where you're in a probability. And then when you measure it, it collapses. And this allows us to do really interesting things where also these quantum bits, also their states depend on each other. So you can't describe one quantum particle, if it's entangled, without the state of another. And that creates interesting things. So if you are familiar with things like machine learning and gradient descent and things like that, you can start building that map of, okay, which problems quantum computers can solve in this arena.
Yeah, that's a pretty great description. I have a feeling we're going to agree on a lot of stuff today. And when it comes to like the problems they can solve, you have to think of them also in terms of use cases. So they are only good at certain things. You have to have an algorithm, right? You have to have something you can actually use a quantum computer for. Those do translate to use cases that have existed already. And quantum computers, we hope, will surpass, attain advantage in those use cases. Like we're doing portfolio optimization now, right, with classical computers. We just hope that quantum will continue to show an advantage in that. Same with fraud detection, different types of use cases that apply the underlying math. Yeah.
Yeah, I think one of the interesting things when I started talking about from this angle, I think this popped out for me because people were like, well, you're wrong. Like Grover's algorithm can search anything faster. And I'm like, okay, in theory, yes. But like, how do you actually map that problem onto a quantum system, right? So quantum chemistry, as we talk about one of the applications that is just very natural. Quantum simulations are just very natural. You take the quantum state and you map it onto a quantum state. You know how to do that. People talk about, well, we can use Grovers for hashing. Okay, I'm like, how do you encode a bit string onto a quantum state? I don't know. A lot of people are looking at different ways to maybe do that, but it's a much harder problem than naturally doing that for a quantum state. So we're seeing new applications in like quantum data loading, right? It's exactly trying to answer that question, like how do we actually map these problems? Machine learning, okay, how do you say, I actually saw a paper a long, long time ago that really helped me kind of dive into this field where they're like, okay, well, if we say like RGB are the different axes, right? Okay, then maybe we can have a mapping, right? You can kind of visualize how that can map onto the Bloch sphere, which is the sphere, the surface area of where that quantum state could be. You can kind of imagine that, but like a bit string is a lot harder to imagine, right? And so you go, okay, so what's the theoretical of like, yes, Grover can speed anything up, but what's the practical? And when you start thinking that way, you go, okay, well, like we mentioned, portfolio optimization is a lot more natural, right? You see that like, adding in a couple features to the quantum state is a lot more natural than doing a bit string.
So with Grover's applied to hashing specifically, I know that gets a little bit of buzz, and obviously not as much as Shor's against the elliptical curve, and for good reason. But even the ASICs today that we have, we're talking triple-digit terahashes per second. So for me, it's okay. For me, like right how exactly would it work, and is it practical? But for me, it's not even just that. Is it even competitive? So if I've got triple-digit terahashes per second in just one ASIC logical unit, if you will, to me that's still that's a very big classical hurdle to overcome for a machine that to be able to run Grovers in order to find a pre-image based on just how much classical competition, because there's a lot of classical competition for that. Do you guys ever think that perhaps there might be more streamlined way to run the algorithm, or do you think, hashing is pretty much pre-image, that's pretty much considered to be quantum secure by almost nearly all quantum physicists. as far as that goes. What do you guys think? Is there an angle there? Is there a attack vector, or do you think it's just going to stay this way for 100 years?
I mean, I think one of the things is I was recently explaining this to a friend, right? And I'm like, and I think sometimes people look at hashing as a encryption algorithm, but like technically, like it's really a compression algorithm in the end, right? Like it's kind of
Loss
different.
decompression.
Yeah. And it's it's meant to be non-reversible, right? Where encryption is meant to be. So it's just a completely different category of problems. So again, if you look at it from the problems, you're like, okay, I can see how encryption, if something is reversible, maybe we can find an algorithm to do it. When something is meant to not be reversible, like it's a different algorithm to figure out like how you could potentially take that back. Like, so it's a totally different thing. I mean, I do think we will get more efficient, definitely in the quantum hardware space, but yes, it is a lot harder of an algorithm. Like besides just the data loading, just the depth of the algorithm and what you need to do. I've talked to a few folks about it who are very much focused in the field, and they're like, it's just, Shor's is already a deep algorithm. Grover's is much, much worse.
Yeah, I don't know if we're going to see practical attacks anytime soon with Grover's. It seems unlikely. One paper posited like 6,500 logical qubits to weaken AES 256 to equivalent AES 128. Then it's still just like a big brute force attack required anyway. So it's the hashing thing. People have asked me all sorts of weird stuff about hashing. One clever, people can get clever. One clever idea was, can you potentially reconstruct files based on hashes using a quantum computer? I was like, well, I don't know. Let's think about that. You'd have to create, random blobs that represent billions of possibilities and then search through those to see if you recreated the file. I don't think so. It's just very complicated.
I could take a stab at that one a little bit. If you brought the bit depth, let's see, SHA-256, if you didn't make it quite as secure, there's a possibility you might be able to reconstruct the file, maybe, but it's not necessarily the same file that you started with. It could just be a pre-image of another of something else, and you just happen to find a collision, right?
Yeah, it's about collisions, yes.
So what for SHA, you'd actually, obviously SHA-256 and all of the modern hashing algorithms are considered to be quantum computer secure, but if it if you had more information or something else, and it wasn't SHA-256, it was something not as difficult. I always thought it was interesting that if you were to solve it, you might not get the same answer that the other person that knows the answer has. You might get a different answer that works just as well. I always thought that was interesting. Let's go to another question. I'll do one more, Ryan, and then okay? So, Anastasia, you were talking about trapped ions, and I know that's one of the biggest commercial. One of the largest commercial, paths that manufacturers are trying to build upon, or platforms is probably a better word. And trapped ions are known for longer coherence times. Essentially, for everyone that's listening, it essentially means the quantum computer is less likely to blue screen. So, trapped ions, it sounds like you're in favor of those. What are the biggest things holding us back to actually bringing these quantum computers to scale? Is it the number of qubits? Is it systemic noise? Is it temperature? Is it the algorithms need to improve their efficiency? What do you think needs to happen here? What's holding us back, and how do we move forward in the industry? Go ahead.
Yeah, definitely. So a lot to cover here. So this is also something new that I have been thinking about for many years, but now we're seeing the results come in. And so, I like trapped ions. They have positive and negatives. Superconducting qubits have positive and negatives. Neutral atoms have positive and negatives. So ions are great because they are natural, right? You don't have a messed up ion like you do when you're constructing a superconducting qubit. However, their gate times are really long. So that's a problem in the trapped ion space. With superconducting qubits, you have the opposite problem where you have manufacturing problems, right, at the beginning. And so you're coding this algorithm and you're like, oh no, qubit 2 is dead. I have to reconstruct everything, right? But the interesting thing that we hypothesized many years ago, but now we're seeing in the industry, is that we're seeing that certain algorithms are going to run better on certain types of quantum hardware. So I've always said, like, I think there's going to be room for a lot of this different hardware to succeed. There's not going to be a winner takes all because of this, what we're seeing. And we've seen that confirmed recently, that we're seeing that quantum machine learning applications, though they are much farther away, are likelier to be better for trapped ions. And that actually kind of makes sense if you are familiar with machine learning classically, right? You're kind of having these neural networks and they connect to everything. Trapped ions are all-to-all connectivity a lot of the time, that like they're built that way, right? Whereas superconducting qubits, you have a lot of a harder time because you have to do a lot of swap gates, which, creates a lot more problems and length of time there. So for quantum machine learning applications, that actually might be a really great application. However, there's these other algorithms that are likelier to work better on superconducting qubits because of the way they're constructed, right? And we can actually optimize the circuit. So again, like there's like, oh, well, it's a negative that you can you manufacture these qubits, but however, that also means you can make those qubits tunable. So you can make quantum ASICs in some way, and there's startups working on that as well, saying like, we're going to co-design these algorithms. And again, as we're seeing that in the trapped ion space, right, we're seeing that they're just generally working better for this set of algorithms. We can also just, in the superconducting qubit space, say, look, this algorithm talks to qubit 1 talks to 2 and 10. How do I arrange those qubits to make sure that we have the most efficient path with the least amount of swap gates, with the fastest coherence time? And we can actually not even think about that error correction issue in the very beginning. So that's one thing there. For all the hardware modalities, I recently did a post on it that got a lot of good results there. Scaling is still an issue across the board. And I really appreciate the companies coming out and at conferences actually talking about this, right? So we're seeing in the superconducting qubit spaces, how do we build big enough fridges? That's a big problem. So worked on that for a little bit. It turns out there's a lot of issues there. So basically for each qubit, you have to have 2 cables to control each qubit. When you get to 1,000, that's already 2,000 cables. 10,000, that's going to be a lot, right? Even seeing, this is a weird issue, which again is like, if you're into the field, this is like the stupidest issue you could possibly imagine. Like the cryostat itself, from the weight of the cables, like the plates start bending and having issues, and then the like temperature goes up, right? So that messes everything up. So there's a few ways that people are thinking about perhaps fixing this issue. So something that we had worked on in the past was actually using a silicon photonics chip as a control instead of doing cable. So you only have the one cable going into the RF to control the RF signals. That's one option. Some people are doing multiplexed work. So that's been going on for a very long time. So the idea of like, okay, you have less control cables, maybe you can control more qubits for that. That's an issue, right? Trapped ions, same thing, right? How do you scale? Okay, so once you have them all in such an array, right, but you need qubit 1 to talk to qubit 100, how do you move them close enough together to actually talk to each other? That's going to take time. That's where the gate time increases. And then also there's another issue. I talked to some vendor and they're like, yeah, how are we going to move it around corners? Like, we don't know how do you move an atom around corners? Like, again, it sounds like a very strange problem to have, but that's a scaling issue we need to think of. And I think this is leading a lot of people to talk about kind of, okay, so we're going to get to the 1,000 qubit era. We're going to have hopefully already solving some good problems around this time. Are we just going to create 1,000 qubit kind of fridges and setups and kind of map those together? So then that means that's something interesting for the algorithms as well, saying like, okay, we may not have a 10,000 qubit chip or something. We may have 10,000 qubit chips. We're going to have to rate the algorithms differently that way. So yeah, there's a lot of things there. There's a lot of like modularity. That's where the photonics come in as well, because you think, photonics is going to be a really good like connector and nodes, so I see this world where it's, a quantum communication system based on photonics that's connected to a superconducting chip to do a certain type of problem, connected to a trapped ion system to do another set of problem, and it's all going to mix together. So I really do think it's not going to be winner takes all in this world. And Yeah, we still have a ton of problems to solve, but this last year, really the last 6 months have been really exciting. And I think, honestly, the AI hype has been really good for the field because we all just sat down and started just doing work in the meantime. And there's been a lot of great results, but still a lot to solve.
So to summarize, the search for a general purpose quantum computer, which is a goal of the industry, might not be as practical. It might be more of a search for the Holy Grail, a little more elusive than we originally think, and that quantum computers are very good at completing certain tasks better than classical computers, but also specific types of quantum computers are better than other types of quantum computers at completing those tasks. And to your point, general purpose QC might not be as quite close on the horizon as we think. That's what I heard you say.
Definitely.
Very well.
Konstantinos may have way more information on this as well, but that's kind of my broad take.
No, those are all real valid points.
Please.
Sure. So in my role, I'm completely vendor agnostic. When I'm designing a use case, I look at performance data on what modality I'm going to try and design it on. Supermark benchmark from Inflection, that's been pretty helpful. You can actually see how different kinds of hardware perform at different types of tasks. Then it becomes an issue when you're thinking about scaling in the future. You're thinking about things like, will there be a winner that takes all? Ultimately, one day there might be. We're talking way out. One thing might just come together for scaling and everyone will sort of jump on that bandwagon. It's possible, right? But that's really, really far away. Closer, we might come up with this idea of there being a limit to how many qubits you could cram into any modality and have it reasonably work. The weight of the plates, that's a good point. Interference from wires. There's all sorts of things that happen that make it just too much noise that you can deal with. So we don't know what that is for any modality, right? It might be 10,000 neutral atoms, but it might only be 100 trapped ions. It might be 1,000 Josephson junctions. Like, we don't know.
To be determined.
But once we figure out what that ideal limit is inside of a box, I do believe it will be a matter of getting lots of those boxes together to make a bigger box, and that's your quantum computer.
Your analogy sounds a bit like Moore's law, in that for a while we were doubling every 18 months or so, but now we're starting to reach, bear with me, 4 nanometers, 3 nanometers separation between integrated circuits. And we're finding that, if I'm not mistaken, electrons are starting to interfere with each other, which essentially is the same thing as quantum tunneling and jumping and essentially messing up those binary signals and creating systemic noise. That sounds a lot like the problem that we have with quantum computers. And Anastasia, I had one question for you. When you were talking about pressure being applied. You're talking about just even small amounts of pressure that get applied to a quantum computer, and then it excites an atom and it gives off a photon, which creates noise within the dilution refrigerator. I was curious about what you meant a little bit more about that. We were talking about compression, because in the quantum computer where you have it's designed to move, just to thermally move a little bit, right? That's with all the coils. Maybe you could expand on that a little bit.
Yeah, there's a lot of issues there. But yeah, even just literally the weight of the cables on the top of the machine is just a problem, right? Like pure weight of just the cables being attached there.
That gives you an idea from a physics perspective just how sensitive quantum bits are. And I use this analogy, and Konstantinos and Anastasia, you guys are great with narratives. You probably have a better explanation for this than I do. But when I think about qubits, what I do is I'm thinking about and trying to explain it, I'm thinking about it myself. I think about them in a way in which I'm taking the qubits and separating them from causality of the universe that we perceive, that where everything is connected to us. I can move around. There's light reflecting. Everything is very, very intertwined at very, very fast speeds. Whereas we're trying to take a qubit, you're trying to essentially separate that. Would you find, is that a good analog, or do you have something? How do you? Essentially, we're talking about superposition, right? So let's talk about superposition a little bit. What's your definition, and how would you explain to someone that's new?
Yeah, well, going back to that real quick, it's even dumber than that. I mean, even, so there's this, you can add magnetic shielding to the cryostat, right? And even just like the way it's plated will cause huge swings in coherence time. So there's actually a big amount of new cryo companies popping up that are working on shielding and plating and all these things just to put inside the cryostat, just because that is so important, right? Like, it doesn't even always come back to the level of the qubits. It's just like the mechanical part. The plate bends, and you have, the one place where something moves, and now the plate isn't perfect, and the one atom has hopped off of it, and now the like everything's terrible, right? So it's very hard to maintain coherence times. I always tell the story of there was the one time we were trying to figure out at 3 p.m. every day, coherence time just went down. Like, why? What was happening? Turns out there was at that point, the sun was coming through the window, and it was hitting one of the water cooler tubes. So the water temperature was slightly warmer at 3 p.m., and that caused coherence times to spike. Like, that's to the level of like sensitivity we're getting into. Like, anything that's not being perfect, like you have to track down in this like entire machine, right? So we had set up this like crazy manufacturing airtable, being like, parts are coming from this supplier. Okay, we put this part in, and now coherence times are up. Okay, what's wrong with that? Like, are the specs wrong? Like, what have we done to it? Yeah, the 3 p.m. problem was just like just so clearly demonstrates how stupid some of these problems that we're dealing with are, and how sensitive these systems are.
Yeah, like Sam Altman walks around with a blue backpack to shut down the machine, to keep OpenAI from taking over the world at any given moment. I would just walk around with a Nest thermometer, thermostat, and just like change the temperature in the room that the quantum computer's in. I mean, it's like, it is very subtle, because we're talking orders of magnitude that of temperature drop, colder than deep space. So it's very easy to mess with that. Absolutely.
As an engineer, this begs I'm a network engineer. I'm not a physicist, quantum physicist, obviously, but I can imagine that, okay, my wave functions collapsed, my qubits are no longer entangled. What the heck happened? Who let the photon in? Where are the electrons? Like, what happened? And then not being able to determine where the noise came from seems like just that problem alone, maybe you guys, but you'd have to have sensors like, I don't even know how you'd set up a sensor system, because there wouldn't be enough noise to find out where it's coming from, and the sensor is actually the qubit itself. And by the time it gets there, it's too late. So how do you tell where the noise is coming from? Okay, so like this type of shielding works better. Do we understand the physics of why this type of shielding is potentially better at blocking electromagnetic interference than others? Or was it even an EMI problem to begin with? Or do we understand like the wavelengths of that are reaching the quantums? Do we understand those things, or is this more of a trial and error process? And this is more of a manufacturing question, so who wants to take that?
Well, there's the manufacturing that Anastasia was talking about, like with the outside shielding. But then in the qubit, it depends on the modality. Like, you can determine how a qubit behaves physically, understand the physics of it, and you can introduce, before we even worry about error correction, you can introduce error suppression, error mitigation, other techniques to understand the things that can go wrong in a calculation, and then kind of like adjust, if you want to really simplify it. It's like a phase flip or whatever that you have to do.
ECC memory. Remember ECC, it had a checksum in it for RAM? Very, very similar to that.
Sort of, except in this case, you're just understanding the things that go wrong, like their actual physical phenomena that go on that subatomic level, and you're kind of correcting for them as it goes. Where you're not actually just checking, you're sort of like also mitigating these occurrences that happen physically right down in the qubit. And they're different, again, by modality, completely different. Some are prone to some are prone to others. Ideally, you want a better qubit before we worry about error correction. That's why things like topological quantum computer are very, very exciting if we can get that to work right. With topological, like a Majorana fermion, this thing is so resistant to noise that ideally, if you had 1,000 of them, 998, let's say, would be error free, and you wouldn't have to worry about error correction. It's pretty hard to visualize, but the idea is if you can get the modes set up correctly, the Majorana modes, you can visualize like a little bridge sort of. And as noise comes through, it's missing most of the qubit all the time. And even if it knocks off one of the pylons of the bridge, you still have all this other like visualized two-dimensional entity that's still there and allowing you to compute. So it's very, very resistant to noise. So topological would be one way to avoid all those types of problems in the first place, if we can get that to work.
Yeah, and diving deeper into the question about the sensors, yeah, it's very hard. And just managing all that, one of the projects I was doing was like, how do we manage all the sensors? Another aspect you have to worry about is how long the chip is exposed to air. So you can also store, how do you store it? So I had a humidity and temperature sensor in the box that the chip was stored out. You put gases into it that hopefully help it, but some point, we just like sent it out for some results, and they're like, yeah, it's been sitting in air for 3 weeks, and we're like, okay, it's pretty much dead at this point. Like we can't. It's not going to be as good. We can do some basic experiments on it, but yeah, this is to the scale where we're still at like very early stage in quantum, right? The theory is beautiful. The theory is amazing. The practical applications and the stuff I had to deal with every day where you're just like, what? Why are they keeping it on air? We told them, we sent them this, we sent these instructions, they're not doing it, can mess up an experiment for months, which is, not that much different, to be fair, at a smaller scale than the semiconductor industry today, right? Like one error in verification on the chips is $500 million and, 6 months to a year lost as well. But yeah, we see that across a lot of the modalities, a lot of the hardware, like the practical implementation is very hard. And I say this with like, people are like, you're a physicist, you should be really good at pool, right? I'm like, I understand the theory, I can do the angles, the execution, the actual like pushing the thing into the cue ball, much different, much harder. I can't do that part. I visualize it very well. So that's where we are in the quantum field.
Yeah, I'm imagining you trying to resurrect a chip now with like little paddles. Clear, boop. They would have to be paddles so small that you could do the Casimir effect with them. Like a physics joke there.
Wow.
I have an old chip here at this point where you just like knew at some point it was dead, and I just took it and I have it, and it's just gonna sit in there forever now. It won't work.
Yeah. Porting over for the next question, we'll take a little bit of a turn to kind of touch more on what you touched on at the end there, Anastasia, of some of the practical stuff, and then eventually like the implementation of this and how we the mass population sees it in the world on a day-to-day. We just came out a few weeks back. We were at Consensus in Austin, and was really pleasantly surprised by a number of really big players, institutions of just coming up to us, and instead of the coming up and being in denial of, hey, quantum computers are forever away, it was more of a, they lead into the conversation with us of, hey, I just, I met with so-and-so from IBM. I was just in Europe and I heard about, this, the quantum threat and how quantum computing is, making XYZ progress. So I'd like to, I was first off, a little, delighted by that, but I want to kind of touch on both of you to see how close or far away are we from potentially achieving quantum supremacy, and along that way, there's a number of hurdles to overcome. I'm not necessarily asking my question on like a timeline of exact, hey, 2028, 2031, 2034, but I know you two both have opinions that myself and a number of the viewers would be curious in hearing what your thoughts are in terms of some of the yard markers to get along the way, and then also from a business impact, especially when some of these people at companies are hearing about it and then bringing it back to their organization. How should they be thinking about it? And I know that's two separate questions, so we can kind of start with whatever on the quantum supremacy front, and then also just how should business leaders be thinking about it in terms of talking to their organization about it. And I know that both of you talk to a lot of people about this exact problem, so I'd love to hear both your take.
Yeah, I guess I'll go first. Supremacy. So I don't really love that word, but I tend to avoid it. And I thought that word was dead. And then D-Wave
It
published
came
a
back
paper.
somehow. Yeah, I
Yeah,
don't
D-Wave
know.
published a paper, and it was right there.
line.
Boom.
Yeah.
There's
It did die like 2 years ago, but I've noticed
yeah,
it
we're
come back.
doing this word again. All right, cool. Thanks,
Yeah.
D-Wave. So now we're using this word again. And I'll start with that paper. It was interesting. It's still under peer review, but basically they were able to show that when doing one version of the icing model, they were able to simulate the movement of these like magnetic poles in a way that a supercomputer would take, millions of years. We've heard this before, obviously, right? Except in this case, the extrapolations look pretty good, and it's pretty hard to poke holes in them. And like I said, it's still under peer review. More recently, there was a little buzz where someone at D-Wave seemed to indicate that, yeah, it could be done with classical computers. So wait and see how that shakes out. But you do get this feeling in general that annealing, which is what D-Wave does, that type of computing, annealing will probably show advantage first, is my gut. I just feel like once the machines get a little bigger, a little more accurate, they'll do better than like digital annealers at solving certain types of problems. So that'll be a type of useful advantage. It's not a universal quantum computer by any means. It's just one specific type of problem. Like a peaks and valleys problem, finding lowest energy state, good for optimization, things like that. So I think that's going to be first, and it could be maybe just one more hardware iteration away from something like D-Wave. I'm not sure. It's possible. So that would be the most optimistic bet I can make. As far as gate-based is concerned, which is what we've primarily been talking a lot about here today, it's going to be a little while. But some things happened this year that I didn't expect. One, I didn't expect logical qubits this year. I just didn't. And all of a sudden, they're popping up everywhere. Everywhere you look, they're popping in and out of existence like virtual particles. We have QRL achieving, it was like 30 some in a lab, but they're going to be releasing 10 this year. And then that's going to switch over to around 30 next year and around 100 the year after. That means we're 2 years away from 100 logical qubits if that tracks out with QR's approach and neutral atoms. 100 logical qubits cannot be simulated with a classical computer. So when something like that happens, you have to wonder, does that automatically bring advantage with it? Because you have something you never had before. So anything you run on it by definition will be something you've never had before. So that's like one potential for where you could just see types of advantage appearing. I know several people who would argue with me on that topic, and I am keeping it very simple for everyone to understand the concept. Sure, there's nuance and everything, but the idea is that we'll have something we never had before. So it's like saying if you have a supercomputer, is that advantage only when you program it and only when you run something on it. Otherwise, it's just a gigantic, expensive thing that's using $1 million of power a month, right? But we will be in uncharted territory. So that I could say with certainty, we'll be in uncharted territory. I don't know if we'll be able to get these things to run well. That's one approach. There's some other approaches. We have the Quantinium work that they were able to get about a 7.5 to 1 ratio for error correction. So they were able to get us 4 logical qubits. They also have the new H21 system with 56. They're not logical qubits, but 56 more reliable qubits that are more connectable, et cetera. It kind of looks like a Dyson fan if you lie it on its sides, or like a big oval with them like running around like a track, sort of.
You knew what I thought you were going to say, didn't you?
What?
Oh, okay. I thought you were going to say sphere. That's been in the news.
Yeah, no. This is just the Dyson, I don't know, weird oval, whatever shape they were thinking of when they made that thing. The headlights of a Rivian. How's that? So these are things that are kind of like surprises. So they could take us somewhere. So those are just points I want to make as far as the march towards advantage.
Yeah, thanks for covering that. Anastasia, anything to add on that one? I think we got a couple more questions that we can dive into as well. Anything else to piggyback on what Konstantinos said, or any differing opinion on that part?
Yeah, mostly agree with it. One thing I do want to point out, very interesting conversations in that we are seeing quantum advantage in some way already from the simulator side. So simulators, right, are to do a true simulator, it's very difficult to do. You're limited to kind of 30 something qubits. What I have been seeing is startups popping up who are making, and this is going back again, this is why I'm very big into next gen computing and ASICs. They're doing application specific simulators. So they can actually get a lot of qubits a lot more qubits out of it by building simulators for specific problems. And from what I've seen, again, like, seeing the papers and seeing some of the results there and seeing the fact that, they're actually seeing monetary business advantage by using application-specific simulators for business. In some way, I feel like quantum is here, right? A lot of people are saying, well, we don't know if quantum will ever work. I'm like, quantum simulators already work and have business advantage that we're seeing. Companies are buying it. That already works for me. So the hardware is going to be there in place when, the company can just like pretty easily switch over at that point. So I think that's really huge. And I've been really seeing that only in the last like 6 months to 1 year that this has been happening. We're seeing those papers come in. Obviously, a lot of these companies are hush hush about it, but I've heard, I've talked to some folks that are like, yeah, we have 200 qubit simulators for a very hyper specific niche problem. But the company that needs it is paying a lot of money for it. And they're saving a lot of money by using our system. That to me is already a win for the quantum industry in general. So now, we're working on the hardware side. I'm very excited this year. Like I mentioned, the last 6 months. Yeah, that QRL release. I remember it was literally had a presentation, I think, from John Preskill that day being like, oh, we still have so long to go. And then the next morning, QRL releases his logical qubit announcement. We're like, okay, very interesting. I do think, there's a little bit of discussion. Again, quantum advantage, what does that mean? Like, I think that's quantum advantage on a simulator. Some people may disagree because it's not on the hardware. For me, I'm like, it's business opportunity. It's saving money. It's having business impact. Good enough for me. I think that counts. Other people may disagree. But yeah, so there's a lot of interesting things, but we're also going to have to talk about like, what is a logical qubit, right? So that's going to be the same thing that we're going to have the same discussion on. I can give you 1 million qubits today. They won't work, but they are qubits, right? So, what does that mean? I can give you, maybe they give us 100 logical qubits, but they don't work, right? So that's not going to have the same impact. But I do believe that they are doing amazing things. QRL has been doing great on that. I do know, I don't think I can talk about it yet, but there's going to be some big news, hopefully in July, for some of these companies that I think is going to be really great again for the hardware. So it just feels, again, like I mentioned, like AI taking over was kind of the best thing. We sat down and we just started doing work in the quantum space, and the fruits are coming out of that this year. And so going back to actually like saying a time, again, I think some level of quantum advantage is here, not on the hardware side, but I do think, 3 years, we're going to see something where you're going to have a real business problem solved on hardware. Might be a small problem, but it's going to be not a toy problem like Google did. It's going to be an actual real application within that time. Long term, Shores is harder to say. For me, Shores is almost like the least interesting problem that we have out there, right? We're destroying, we're not creating. So I'm very happy with just the timeline. People are saying, early 2030s for Shores, which has been interesting as well. Things have been accelerating on that side as well. So I do want to talk a little bit about the Alice and Bob experiments. So they have been, they released a paper, I think last year, talking about doing Shor's algorithm in 8 hours using 100,000, 133,000-ish cat qubits, right? So it used to be 10 years ago, we said we needed 10 million qubits. Now it's a lot less, right? So orders of magnitude are hopping down on both direction, right? So the hardware is scaling up or figuring out these scaling problems, but also working on the error correction side as well, right? And things are being brought down, and you're seeing this interesting little graph, right, of when's that crossover going to be, when we're going to have all the error correction in place, we're going to have the hardware in place to actually hit that like advantage.
Yeah, no, thank you for both covering and elaborating on that part. I think wrapping up the first or the last few minutes, at least of this panel segment, I think it would be nice to kind of do a little bit of a couple more questions, kind of a little more speed round style of not necessarily jumping into the meat of everything for 10 minutes each, but more so just giving whether it's your current thoughts on it or, something interesting that you've read. I know you both touched on some interesting work and stuff that you're seeing in the current day in the last 6 months. But one part that I think you touched on twice, Anastasia, and I want to hear from Konstantinos and then from Anastasia on this is with, quantum computing, progress being done. How do you see that blending and differing in terms of with other emerging tech like AI in the blockchain space? Anything interesting you're seeing in terms of, okay, hey, well, this with a combination of AI plus quantum, that might open up some windows here, or, oh, actually that area where they're talking about in the news, that's just a lot of fluff and hype. What's your hot take in a condensed version in terms of like what you're either curious about or in terms of like what you're paying attention to each?
Sure.
Whoever wants to start this one.
Yeah. So with the AI thing, if you had asked me a few months ago about quantum and AI, I would have told you AI is always one of the big use case pillars of quantum. Quantum machine learning of some type is always something we're shooting for. Fraud detection, whatever. There's always something there. But now more recently, there have been implementations of crude quantum transformers, and as you know, transformers are the brains behind LLMs, so to speak. So there might be something interesting there in the future. Too early to say, but that's kind of exciting. It's at least a reality. And as far as blockchain, well, quantum was always just a big threat to blockchain. Let's face it. I believe that it'll threaten blockchain before it'll threaten RSA. I think we'll need fewer qubits to attack, let's say, Bitcoin wallets than we will RSA.
Yeah. Awesome. Anastasia?
Yeah, on my end, just to reiterate a little bit of these interesting hardware applications or hardware modality wins that we've had, the QRL, logical qubits. I want to see, and I'm hoping to see more and more people diving into these application specific and actually testing them between hardware. So there's platforms now set up where it makes it a lot easier to test between hardware modalities, because that's a huge problem, right? If you're writing code for a superconducting qubit versus trapped ion, it's going to be completely different. It's going to be different between different chips that you're running. So just being able to finally do that, I think there's a huge opportunity there for researchers to kind of dive into that and really push this part of the field forward.
Thanks. I think one part I want to leave us with, and I'll pour it over to Michael, then maybe ask one more as we wrap up, but I want to leave the viewer with something that they can, I'm sure a number of them have already taken a couple notes and are going to go down their own rabbit holes based on the knowledge that both of you shared just in our dialogue here. But I'd like to give each of you just a moment to, if you either want to inform the viewer on something that you're like, wow, I just came across this last week, or if it's a research or a paper, it can be anything from a short tweet that you found intriguing, or it could be a specific thing of, hey, read this research paper on this. Send our viewers down a rabbit hole. It could be anything big or small. With this being a post-quantum panel, our hope is to have a reoccurring cadence where every few months we bring you as guest panel experts back on. So it's not this isn't the only thing they're going to be hearing from you in the the coming year or so. So what today in mid 2024? What's a piece that you'd like to share with them?
For mid 2024, the first thing that has to leap to mind for me is any minute now, we're expecting the NIST standards for post-quantum cryptography. We didn't really talk about that today much, but this is going to be the big thing that affects literally everybody. It's Y2K all over again. It's going to trigger a sequence of actions that everyone's going to have to actually start taking. First, federal agencies, but we expect the private sector regulators to largely just take it and run with it too. So if you're involved in information security in any way, shape, or form, visualize Heartbleed meets Y2K. It's going to be a lot of work, a lot of implementation, a lot of getting things done over the next few years. So that's the biggest one I could think of right now that's coming.
Yeah, and we could do, literally the four of us could do a whole episode just on any of these as is, but Anastasia, I poured it over to you for this one.
It's a big deal.
Yeah.
Yeah, it's a huge deal. And I think it's a big opportunity for startups as well, because how's a bank that has their systems running on COBOL and have no COBOL engineers going to upgrade, which concerns me a little bit with banks in general and all the older institutions. So definitely something I am keeping an eye on. I mentioned a bunch of papers. So actually, maybe I can do a call for viewers to help me out with this. And maybe this is a new episode for us to do. I am concerned about that. Actually, I was reading the blog post you guys were working on, right? The Taproot update of Bitcoin. I'm trying to understand it deeply, right? So the idea that it's actually this Taproot update for Bitcoin is actually going to be even less quantum secure than it was before. It's hugely concerning to me. I really want to try and understand that a little bit more. And so that's something I'm really keeping an eye on. And no one's really talking about it yet. So I do definitely want to do a deep dive. So open call to people. Find me on Twitter or anywhere else. Let's chat.
Yeah, I could see even a live one where we even, get a little interaction going with that in the comments to see. But no, thanks for that. Michael, I'll port it to you as any last questions. I feel like anything from here will segue into an upcoming one, but that's all I have on my end. I'll close it out after you ask anything else, Strike.
Yeah, obviously Anastasia and Konstantinos bring a tremendous amount of knowledge and expertise. Anastasia, I got to admit, I was a little jealous when I was hearing you describe physically working on the quantum computers and having the physical access and being able to see with your eyes. There was a little bit of jealousy there at the time. One thing I did hear, as we were talking about the physical nature, the machines themselves, the improving decoherence times, ice shielding, all of those things that we're doing in order to get us to a point to where quantum computers are much more standard, are much more reliable. One thing I didn't hear us discuss, which I think is an underrated term in the industry, especially when you're talking about information security, is Mosca's theorem, right? So it's and I know you guys know what it is, but for the listeners, essentially what it means is if you have information that you need secure for the next 10 years, let's call it 10 years, and you think that, let's say within the next 10 years, you can run the numbers yourself, you give it a 10% probability that maybe the quantum computer would be able to decrypt your ciphertext in the future, then you have to objectively look at that and say that that's a huge risk, that 10% risk of having your data now that's being encrypted now. And I can guarantee you that there are people that are just scraping data off the web. They're saving the ciphertext. It's called store now, decrypt later, or harvest now, decrypt later, depending on which side of the Atlantic pond you're on. But this is happening now. And if you want to be able to be post-quantum secure, you can't just be thinking about the hardware and when we're going to get there. In a lot of ways, if we're talking about data integrity, we're there now. You need to start thinking about this now, because if your data needs to be secure for the next 10 years, this has to be a concern now, because there's nothing to keep the ciphertext, the packets. And as a network engineer, I know how easy it is to jump into a Cisco switch, create a span port, dump all the frames to Wireshark, save a PCAP file, and walk off. I mean, obviously, setting up a span port takes network access, but that's besides the point. The point is ciphertext is public. It's already encrypted, so there's no reason to really keep it encrypted, to keep it away from taps and things like that. So I think that, and I can speak from experience, nobody is talking about the quantum threat in corporate. At least for the customers that I have not heard anyone bring it up as a network engineer. Not probably maybe once every few years I'll hear someone even say the word. So this is really running under the radar, and Mosca's theorem is really running under the radar. But that being said, I wanted to thank you, Anastasia and Konstantinos, for being on the show. You guys, it's always a pleasure to have you guys on. I love talking to physicists. I get passionate about it, and I want to thank you so much. Off to you, Ryan.
Yeah, no, likewise, enjoy the conversation. I think hope the same for you. I think we have an audience that's already engaged and enjoys this content. So both of you being able to join on together and collab, it's 1 + 1 = 10 type of collaboration in terms of feeding off each other on answers. But I'm sure we'll get feedback from our community, different social, on what their thoughts were, what questions they have for an upcoming panel of a couple areas where we could have talked on as well. As a closing out thing, where's a good place for Konstantinos and for Anastasia, a great place for everyone to find you? I know the classic, hey, just Google your name, find your social from there, but what's 1 or 2 places where you'd like anyone, if they want to jump in to see some different work, where'd you like us to point them to?
For me, it's just Constant Hacker with a K.
On Twitter
platform, and you can check out the Post Quantum World podcast wherever you listen to podcasts.
Cool. Awesome.
Yeah, for me, A Marchenkova on everything. So you can find me anywhere there. Definitely trying to post more on Twitter these days and do some of these longer form posts again. And just really share more about these kind of the next level of quantum, right? I have a lot of blog posts on my website, amarchenkova.com, on the basics, and then posting on Twitter a lot more of these new insights that we're seeing in kind of this new era of quantum.
Awesome. Well, we look forward to hopefully doing this again in a recurring kind of panel style. For those viewing, if you check in the show notes, I'll drop Constant Hacker, A. Marchenkova, their links for some of their, to see their work. Just go in the show notes of this episode and you can click directly to them and their work as throughout from there. But just like Michael said, Konstantinos, Anastasia, thank you so much for joining us. And for everyone watching, make sure to keep those digital assets post-quantum secure and have a great rest of the day.